Benzene all by itself is very stable because it's aromatic. It allows the electrons in the p orbitals to move in waves that only have one node, and that means that it's more stable than a molecule with the same number of conjugated pi bonds, like hexatriene, because this molecule, the electrons in the p orbitals there have to move in at least one wave that has two nodes. So benzene by itself, because it's aromatic, is especially stable. And what that means is it's not very reactive. What is reactive is a carbon bonded to a benzene ring. It has to be immediately bonded to the benzene ring. That carbon is really reactive, and that position is called the benzylic position. Any carbon that is one atom away from a benzene ring, that carbon is in a benzylic position. And it'll tend to be really reactive because any high energy intermediates that you form there are stabilized through resonance with the ring. The ring has those parallel p orbitals going all the way around that the electrons are able to fly in. That's why they can move in unique wave patterns that stabilize them. If you have a lone pair here, that lone pair exists in a parallel p orbital, and it's able to spread out through the whole ring, which stabilizes it. If you have, instead of a lone pair, you have another high energy intermediate, like a carbocation, that's an empty p orbital, and that can be stabilized because the electrons in the ring can move around and bleed into it and help stabilize it a little bit. Or if you have another high energy intermediate, like a radical, an unpaired electron, that is also existing in a p orbital, and is able to be spread out in the ring through resonance. So if you want to use resonance terminology, you can look at those and say, this position here is allylic. It's one atom away from an atom in a double bond. It's allylic to the ring. And so any high energy intermediate you form there is going to be stabilized. So if you need a high energy intermediate to make a reaction happen, then that reaction is going to be favored at the benzylic position, because that position can stabilize that intermediate. Now, there are several different reagents that you can use for this. What exercise 1819 is asking you about is specifically chromic acid. That's H2Cr2O7, and sometimes you may see that same sort of recipe expressed as sodium dichromate, so Na2Cr2O7, and they usually mix that with aqueous acid, so water and sulfuric acid. So those two things will affect the same thing. They will turn the benzylic position into a carboxylic acid. And this is a harsh, a nasty reagent. It is not gentle on a molecule. It will tear everything off. It will replace anything at a benzylic position with a carboxylic acid. It's like throwing a bag of piranhas in with your molecule. So if all you have is just a methyl group, like here in toluene, then if you treat that with chromic acid or sodium dichromate in the presence of aqueous acid, then you'll get that same molecule just at the benzylic position. You'll have a carboxylic acid. So strong oxidizing agent. You're forming lots of new bonds to oxygen. This carbon now is bonded to as many oxygens as it can be while still being attached to the benzene. So chromic acid, sodium dichromate, strong oxidizing agents. They'll turn vulnerable things into carboxylic acids. What we've seen so far is primary alcohols. That's usually what these strong reagents are turning into carboxylic acids, but right now they're reacting at this benzylic position. And the truth is, people are not yet sure about the mechanism for how this happens. They do know that in the first step involves a hydrogen at the benzylic position, and that hydrogen gets pulled off in a radical reaction so that you form a radical intermediate. This hydrogen goes on to react with something else, but they do know that you form a radical there, and that you need a hydrogen there to pull off to form that radical. And the reason why they know that is because this reaction does not work if there is not a hydrogen at the benzylic position. So for example, if you had a tert-butyl group, here's your benzylic position, that carbon does not have any hydrogens on it, that would not turn into a carboxylic acid. So this chromic acid, or sodium dichromate, will turn the benzylic position into a carboxylic acid unless there's no hydrogen on the benzylic position, in which case it stays exactly as it is. This does nothing. Okay, so if you know that, then you'd approach this molecule, you'd identify the benzylic positions. Those are the carbons immediately bonded to the benzene ring. If you treat that with chromic acid or sodium dichromate in aqueous acid, in either of those cases, that turns both of those benzylic positions into carboxylic acids so long as they have a hydrogen on them. So let's draw the benzene ring. Does this benzylic carbon have a hydrogen on it? Yes. So it gets turned into a carboxylic acid. Double bond to oxygen, single bond to OH. Does this benzylic have a hydrogen on it? Yes. So it gets turned into a carboxylic acid. Double bond to oxygen, single bond to OH. And notice how intense that reaction is. You kicked a carbon off. Originally, you had 2 carbons. Now you only have 1. What happened to the other one? It got oxidized to carbon dioxide. This thing is so harsh, it turns this other carbon into just carbon dioxide, oxidizes it as far as it could possibly get, 4 bonds to oxygen, and that bubbles away. That's not what we're interested in. We're interested in how this carbon chain is going to change, so you don't have to draw that. What you would want to draw is what's left of this molecule, and that's both of the benzylic positions that have hydrogens on them get turned into carboxylic acids. So just to illustrate that one more time, if you take this next molecule, and let's see what it looks like. Just originally, you take that weird molecule, and you're like, okay, chromic acid. That's either H2SO, that's either H2Cr2O7, or you could have sodium dichromate in aqueous acid. And in either case, both of those are really strong oxidizing agents. They're going to turn all benzylic positions that have a hydrogen on them into carboxylic acids. So let's draw our benzene ring, and let's think about each of the benzylic positions one at a time. Oops. Okay, so first, the benzylic position on the left. The benzylic position is the carbon bonded to the benzene ring. Does that carbon have a hydrogen on it? It does. And so that carbon is going to turn into a carboxylic acid. Double bond to oxygen, single bond to OH. Let's think about the next benzylic position. This carbon right there is on a benzylic position because it's immediately attached to the benzene ring. Is it also bonded to a hydrogen? It is. So that whole thing, forget the crazy carbons on it, the whole thing just gets turned into a carboxylic acid. Double bond to oxygen, single bond to OH. Notice you lose a whole bunch of carbons. Those turn into other molecules in the soup of your mixture. The molecule with the benzene ring on it turns into a carboxylic acid. Next benzylic position. This carbon is on the benzylic position because it's immediately bonded to benzene. Is there a hydrogen on that carbon? There's not. That carbon already has 4 bonds drawn, and they're all decarbons. Because there's not a hydrogen there, the sodium dichromate, or the chromic acid, is not able to react there. It needs to form that hydrogen radical in the first step. That's the only step of the mechanism people are 100% sure of, and that's clear and simple enough to discuss in organic chemistry 2. So, because there's no hydrogen there, these reagents will not work there, and that branch stays exactly the same. So the big takeaway here is chromic acid or sodium dichromate are strong oxidizing agents. They'll react at the benzylic position, not on the ring, which is aromatic and therefore very stable, but at the benzylic position. They'll turn any benzylic position into a carboxylic acid unless the benzylic position does not have a hydrogen on it.